the moment, Mr. Thomas Hammer, for his first talk.
So Telnet is the reason why SSH was invented, more or less, because for some time we used Telnet in the past to log into remote machines, but back in the time when Telnet was a thing, it was mainly used on university campuses or in private businesses when the internet wasn't so prolific. So now that the internet has become more and more connected and more people are sort of connecting their businesses and their university campuses to the internet, a lot more traffic's being passed over the internet rather than staying inside of local area networks. So the important thing to know about Telnet is everything in Telnet is passed in plain text. So remote administration is pretty much these things right here. So opening a remote connection to a remote machine to run commands, running scripts, troubleshooting, starting or stopping applications and services, and adding and removing users and privileges. So in the past, we used Hyperterminal or Telex on Windows to remotely administer LANs and access remote servers. The majority of people were pretty much clueless about internet security back then, and hacks weren't really a thing back when Telnet was being used for administering people's local area networks. So you knew who was using your LAN when you were administrator for a university or a business. You knew who was on there, who had access to it. It wasn't like you could just jump into that service from anywhere like you can now. So by the time people started to figure out how the internet was working and what it can do for them, people were discovering that things could be bought and sold online. With the advent of online shopping, payment details, credentials and whatnot was being passed around in plain text. So here you can see a screen grab that I've taken from Wireshark on my computer. Each of these lines you can see here is a packet that's been passed across from my local terminal to my router. So you can see one packet was passed back as a login prompt, and you can see that that's just plain text, unencrypted. So the next one is me typing A for admin to log into this. So each of those packets you see there down there is one character being typed in, and you can capture all of that and see what's happening just in plain text. So in the beginning there was modems, and 2800 baud modems could be bought for about $900, and in today's money that's like $2,040, which is a lot of money for a modem that does 240 characters a second. All of these web pages that were built in the sort of 90s were built for speed, because the transfer times for web pages to load took so long. Some pages took up to a minute to download to your web page to draw on the screen. So most web pages were built back in this time so that they would have the least amount of overhead possible, and that means that encryption was definitely a second thought, because speed was of the most important thing. So these transaction details are being passed over the web between the client and the server as plain text. That's the main takeaway from this. And now we're going to see Tatu Ulonen, the Finnish guy who invented SSH, give a brief talk about his technology that he invented.
Hi, my name is Tatu Ulonen. I'm the founder of SSH Communication Security and the inventor of SSH, the Secure Shell. It all started 20 years ago when I was a university researcher and there was a hacking incident in our university network. Somebody installed a password sniffer on the network, a program that listens for network traffic and intercepts usernames, passwords from the network traffic, which hackers then use to break into other systems. And when it was discovered, there were thousands of usernames and passwords, including some from my company at the time. And I started thinking, what could I do to make the network more secure? How could I use computers from my home, from my office, from the university, without having to worry about somebody getting my password? And so I started learning cryptography, on networking, and in the next 3 months wrote the program called SSH. which I then published as open source in summer '95. And in a few years, it basically spread throughout the whole university community, research community, enterprise server infrastructure. Today, it's being used on hundreds of millions of systems, every Linux system, every Unix system, every Mac, router management, network management, configuration management, file transfers. It's everywhere. More than half of world's web servers run on servers managed using SSH. The cloud infrastructure that runs the services that we all use every day on the internet is managed using SSH. It's everywhere. It's the backbone for securing the internet and modern information systems.
Thanks, mate. So Wireshark was released in 1998, which was just a few years after SSH. And we can see that SSH was built to fix a security flaw that was Telnet. And it fixed it by encrypting all of the packets that are being sent in a secure tunnel between the 2 points that were set up. SSH was said to be a short-term fix for Telnet, and it was not more widely adopted because people were saying that SSH would be broken in not much time at all. And surprisingly, it's the last one standing from all the technologies that were thought of at the time. I suggest you Windows users out there migrate across to using OpenSSH as well. You can get OpenSSH on the command line now, and you have been able to get that for some time. Don't use PuTTY, you don't need it. So we're now going to cover some of the concepts around SSH, starting with some simple bits regarding Debian distributions. So just for anyone who's not sort of very Linuxy, this is all the different kinds of Linux distributions they are, and the tree that represents where the nexus of those Linux distributions are, where they came from. So Debian is basically the top third. These are all the Debian distributions, and somewhere in here is Ubuntu and Mint and these types of distros. So you don't need to install SSH unless you're on a Windows machine, and it comes pre-installed on pretty much every Linux distro. You can check its function using this service SSH status command. To install the server, enter this command here, sudo apt-get install OpenSSH server. And then with the next command, you can check to see if the server is running. And SSHD will be running by default on port 22. And that's where most SSH servers run from. Although it's highly advisable if you're going to run your own OpenSSH server that you put it on another port, a higher port, and I'll show you why that is later on. So authenticating with SSH involves the three-step process where the public keys are exchanged. There's an authentication process that we'll cover next, and there's an agreed symmetric key which is used for the session. On the right-hand side, you can see the symmetric ciphers, the hashing functions, and the key types. These are all the ones that are supported on my machine that I've got at home. So symmetric key encryption has one key, and all participants in any conversation with symmetric encryption have that key, and that key is used for encrypting and decrypting the message that's going to be sent out to all the other people who are involved in that that session. So it's important that session key is kept secret amongst those people who are involved in it. Nearly all communication that happens on the internet is done through symmetric keys. So TLS runs on this exact system that I'm about to show you right now, and pretty much everything uses a symmetric key to communicate because of the speed involved in how fast it can encrypt and decrypt those ciphers. A good example of a symmetric key in a matter like ROT13 isn't exactly encryption, but it's a good example of a symmetric key because everyone knows that you rotate the characters 13 steps to the right or the left, and then you'll get an encrypted message, and to decrypt it, you just go 13 the other way, and you've got a decrypted message. So the question really now is, how do you get this symmetric key that you can pass between you and the other person you're speaking to without anyone who has access to that domain that you're broadcasting on seeing it? And the answer to that is on this next slide. Asymmetric keys. So these keys involve having two keys, a public and a private key. They're generated on your local machine, and the private key has to be kept a secret. Both keys have the ability to encrypt a message, and the other key, the opposite key, can decrypt that message. The function of that, though, is that a public key is used to encrypt messages that only the private key can decrypt, and that's used for sending a secret message to the key owner. So if I have your public key, I can encrypt a message with your public key, and then only you with the private key can decrypt that message, and only you. The difference is with using a private key to encrypt a message is that the public key, which everybody has, can decrypt that message. And the reason that you want to have something like that is so that you can sign a message to say that that came from you. That's guaranteed. If no one else has your public key, your private key, that anyone who has your public key can guarantee that message was only from you. And public keys should really be exchanged out of band when you're communicating with an end server that you want to authenticate with. It's not a good idea to upload directly, and we'll see why on the next slide. So it's time for my live demo now, I think. So, okay, so this looks really cryptic and really difficult to understand, but if you understand, does anyone here not know what a modulo is? If you modulo something? Okay, so modulo is when you make a division of a number, it will give you a number of times that will divide into that number, but the modulo of that is what's left, the remainder. So the something divided by something remainder what is the modulo. The what's the modulo. So that number is generally quite a small number. So what happens is in Diffie Hellman, which is the main encryption method used by pretty much everything you touch, your phone, your computer, you name it, everything uses Diffie Hellman key exchange. It has in the domain of the public, you've got these two G and P numbers. So in this case, I've used really small numbers, so it's reasonably easy to follow. So the G is a generator, which is a random number that's generated by the two parties. And the P is a prime number that's a random prime number. Doesn't matter what it is, it's just got to be prime. Each of the people who want to communicate a message have to have a private variable. In this case, it's X and Y. So one person has a 4, one person has a 6. And then you say the G, which is 2, to the power of, in X's case, it's 4, which gives you 16. The modulo of that, 11 equals 5. And then you take that 5, and then this number 5 then becomes a public variable that you can pass to the other side. And when the other person gets that message, they run the exact same algorithm as on the bottom there, and that gives you an output of a certain number. And that number that you share between people, which ends up being, after all of this, the shared number from going from 1,4 and 1,6, you get a shared key of number 5. So I'm going to help you understand exactly what's going on here, but in my demonstration, there's not going to be a prime number. So this is just going to be, there's no modulo involved in this because you can't modulo colors, right? So bear with me. So imagine for a moment that what's on this, the inner side of the table is the public domain. So you guys can all see this as the public. Then, no, it's okay. So, and then imagine, actually, yeah, come on, Eli. Okay, so just imagine, actually I've got this the wrong way around. Just imagine for a moment that, well, in actual fact, these are the exact same color. They're just measured out so we can do this like in a more sort of scientific way. Imagine this is the same container. So what happens is you've got two public variables, which is the G, the generator, and the prime number. But in this case, we're going to just discount the prime number. So what happens is all of you guys can see what this color is. And if you know anything about RGB values, you've got like, you know, a number correlating to a color. So this is how it kind of like how the analogy works. So what happens is I have a public generator, which everybody knows. You can all see what it is. You can't see what this is. I take the generator and I put it into the private domain so no one can see it. And you can do this too, like grab the generator. So I take this out of the public domain so no one else can see it, and no one can see my private X variable. and no one can see Eli's private Y variable. So take one of the colors and dump it in the glass. And this gives you the A, right? So we've gone from having an X to an A, and you've gone from having a Y to having a B. Both of these then get passed back out into the public, and there's no way you could tell what color this started as by seeing what it's been mixed with. There's just no way you could say it could. It could have been yellow. So it could have been red. It could have been a bit more orange. Could have been a bit of something else. You can't say definitively that color started out as a specific RGB value, for example. So we take these and we swap them around. I take mine. You get that one. This one comes back over here, and then these go out of the public domain into the private domain. So from now you can't see what these colors are anymore, and then you dump in the other one. And that goes very dark. I should have rehearsed this one. But basically, these colors end up being the same color. The food dies a bit too much. But you get the idea, right? So these colors are actually pretty much the same color. And they're the same color because that's how it mathematically works. In reality, this type of work is done by a very specific mathematical function which will always return the exact value, which is why you get this is how it basically works. And then this value here becomes the key used in the symmetrical encryption. So when you have symmetrical encryption set up, the key that you generated here is the one that will be used that you pass your secrets across. So sorry? Well, that's all this is a key that services like, for example, the AES encryption scheme, right? So AES is actually a symmetric encryption cipher which is used, and you need to provide that with a key. But now both Eli and I both have the exact same key, so we can use the exact same key to start encrypting messages together. And that's kind of the point of it. I hope that made sense. Did everyone kind of follow that? Yeah? Okay, so the next slide I'm going to show you is a variation of what you've just seen here, but rather than using a generator like this and a prime number like this, there's points on a curve that are used to do the exact same operation. I'll give you a point on a curve, you give me a point on your curve, and then we do some mathematics to it, and then that gives us the same shared secret in pretty much the same way. But this is called elliptic curve cryptography or elliptic curve Diffie-Hellman. So don't let the curves like intimidate you too much, but basically you've got a P and a Q, and the P and the Q are public variables, much in the same way that the generator is public and the prime number is public. In this case, the P and the Q are public variables that are passed to everyone who can see it, and then the intersecting line between the P and the Q will give you a spot on that curve. You flip it over to the other side, and then that gives you 0.1. But then what happens is you also pass a number of bounces across, and what happens is you bounce from R negative to R positive, and then you draw a line between the R positive to a P, and that gives you a new intersecting point somewhere else on that curve. So this one actually here describes how that bouncing around happens. So it goes between 2 points and then goes back here, and then something else. The next iteration of it will go from that point to the next R negative to a new point Q here, and you can basically they provide a number of bounces that you do through each of these triangulations, and that gives you the same effect as to what just happened right in front of you. It's just that the way that this gets done with elliptic curve Diffie-Hellman is that the key sizes can shrink down to a very, very small number. With elliptic curve Diffie-Hellman, you get key sizes that are significantly smaller than RSA keys. So the takeaways from this is something like this. You've got ephemeral and perfect forward and secrecy. So RSA, which is the encryption method, the asymmetric encryption method's been used for many, many years, always generates the same number at the end of the exchange. So when you authenticate using RSA, you get the exact same number. that means you get the exact same RSA key, AES key, and that means that every encryption, every session you make with another partner gives you the exact same key to unlock that AES algorithm. What that means is, if someone can get a hold of your key in future or break your key in future, if they've captured your data from beforehand in any way, they can go back and read every single message you ever sent using that encryption key. So my advice to you is, if you're using RSA keys now, you don't have to, move across to one of the newer algorithms. In this next slide, here you can see symmetric outlines like AES, which is what we described about having the symmetric key where you and I both have the same key which can decrypt and encrypt. The key size for that, it tends to be quite small. Also, it's quite fast to encrypt and decrypt, which is what everything uses on the internet mostly. But to get to this, you have to use one of these. So elliptic curve, which we just covered quickly, is much smaller than the equivalent size RSA key. So this RSA key at 1024, which do not use a key this size, they're totally unsecure. And these are generated in about 1 second. So the computational power required to generate an RSA key of 1024 bits is about 1 second. Also, these numbers for generating this size key, these were worked out on a Core 2 Duo, which is really, really old. If you were to do this again on, say, an i9 or something very, very new, these numbers would just be like an order of magnitude smaller. But nonetheless, the time it takes to generate like some of these larger keys can be like 7 hours or more. And there's not really any sort of hard cap on RSA key sizes, but this is computationally heavy the bigger you get. If you have a server that's running that has, well, if you have your home server, it doesn't really matter too much because you know who's accessing it. It's probably you yourself and maybe one other person. But if you have like a work server that has like hundreds of people authenticating to it, and it has to spend some amount of time decrypting a key that you've sent to it, just so it's secure, you want to go bigger and bigger, the load on that computer then gets like higher and higher. So you want to kind of stay away from too big RSA keys because the load just increases exponentially. So that's why I'm kind of advocating for using elliptic keys, elliptic curve keys. I do. So we can see here each of the auth methods available for using keys, as well as using keys. So there's different kinds of, for SSH itself, you can use an API service, host-based keys, keyboard interactive, meaning you can type a password in basically. You can also go with no authentication if you've got a public server, passwords, and using a public RSA or elliptic curve key like I mentioned earlier. And we can use several methods chained together that will sort of provide some version of multi-factor authentication, which is just built right into the SSH program itself. It's not really multi-factor, not truly multi-factor. It's more that you've got several kind of gates to get through. So in this particular instance here, authentication methods, public key, password, host-based means that you would have to give a key first, a public key first. Then you would have to provide a password after that key's been authenticated. And then lastly, there's some host-based keys that will get passed across as well that need to match up with the keys that the server's expecting. So RSA is still used everywhere, but as we've seen, it's not a good idea. But if you have to, use bigger numbers as the default. Pretty much, if you're not using at least 3076 size keys, you're vulnerable to someone breaking that key just through brute force, basically. The default key, I'm pretty sure, is 2048 bit keys, I think it is. But generally speaking, if you have to use RSA keys, you want to use a key size at least 4096 bits. And you can stipulate there by saying -B, which is the bit size, when you use the key generator. So if you have more than one private key or a key set on your system, you want to be able to stipulate which one you want to use for each connection. And the way that you do that is you specify it with the I flag, and then you provide the path to that key. By default, though, SSH will look in your .ssh directory, which is a hidden folder. for any key starting with ID underscore anything after that, which could be DSA, which is now deprecated. It could be RSA. It could be EC elliptic curve keys and ED255 keys. Opera uses SSH. So when you follow the prompts and set a name, optionally you can set a password for the key itself. So these are the 4 encryption methods, and then you can choose to say DSA, RSA, ECDSA, and ED25519, depending on which one you want to use. With the -T flag will give you that. Generally, I would recommend staying with something like an ED25519 key because it's the newest standard that's out at the moment. Don't use DSA, it's deprecated. Don't use RSA, even the SSH wiki page says that the Snowden leaks prove that the NSA and whatnot, government organizations, can actually break these RSA keys. So SSH communicates over sockets, just like everything else. Being able to recognize what's happening here is important. So we have private IP addresses which start with 10 dot something, 172.16 dot something, and 192.168 dot something. These are private network addresses that exist inside of what's behind your router in your private network. It's public addresses, which is pretty much all the other numbers, more or less. And then there's the loopback and addresses, which is 127 dot something. But 127 dot something is the same, functionally speaking, as using localhost as the name. That's kind of important to follow what's going on there as well. So in SSH, generally people kind of drop this first. Sockets is, for those of you guys who don't know, a socket is an IP address with a port number. In SSH, we generally don't include the first part of the socket, just normally the port number will do for the first part of it. I know why you're laughing. So in this slide, so we want to know how do computers in a private network talk to computers that are outside of that private network. So if you have unsolicited traffic come up to your router and try and get through to your web browser, for example, on port 80, your router will just block that out and it will drop those packets. The way that you get traffic through your routers, you have to set up port forwarding. So what's happening here is this and this are pretty much the same thing, but on opposite sides. And in the middle, your router says what can come through and what can't come through. It's basically your kind of firewall on your router. So if something hits port 22 externally at your public IP address with an address of port 22 as part of the socket, and you have port forwarding set up to go forward to your next computer, that will land on port 22 at your at the device you set it up to. But if you don't have this port forwarding set up, you can't get access to the computer you want to access at home or on behind a Bastion server, for example. So this is a really important topic to understand. When you've got NAT, network address translation, you can't just get through to any computer that's out there. It has to have a public IP address and an available socket. Yeah, exactly, a static IP address. I'm actually going to get to that. I should have said that earlier though, that's right. So you have to have a static IP address because if you don't have a static IP address, basically that changes as your ISP dictates every couple of weeks or something. And then the address you thought you had is no longer your address. Also, if you have carrier grade NAT, which a lot of internet providers have now, you literally can't get access to that box because you share that IP address with a bunch of other people, and your provider will basically have NAT set up in such a way that you can get out to the internet and traffic can get back to you, but you can't actually get into that computer. You can actually put a request into your provider, but generally speaking, most of them will ask you for extra money to get a public IP address. So you can think about your the ports as being actual ports, something like this. It works in much the same way. So in this case, Thomas is optional, as the remote machine's user account has the same name as the local user account. The user accounts will fall through. So in this case, if I want to SSH to this address here, this is a public IP address, I can because my local machine, I'm logged in as Thomas at a private address, I can just type in that IP address and it will still drop me into a Thomas account at the other side. So once a key pair is generated, the public key needs to be sent to the SSH server, and the private key needs to be kept secret on your computer, and don't share it with anyone, right? So an important note about this file, it needs to have permissions for, no permissions for any other users or groups on your computer. So you need to use this command chmod, which modifies the permissions for that file to say, like, numbers 1 through 7 will do. What that means isn't important, it's kind of out of scope, but basically the 2 second numbers means groups and other users, and you want to have no permissions for those, otherwise SSH, the server, will bounce that key from you, and it won't work. So after you've sent your public key to the server, you should turn off password authentication in the SSHD config file. If password authorization is left on, you'll have hundreds of attempts per hour from Chinese bots trying to break into your service. It will not stop. I had my SSH server at home set up on port 22 for a couple of days, and my auth log was out of control. I just had hundreds of attempts from random IP addresses all over the world trying to break into my service, so I had to change to a higher port number, which sort of made that abate a little bit. Adding keys that have passwords on them will stop SSH with the agent. So on your computer you'll have an agent, and if you add your keys to the agent, it'll stop SSH asking you for the password every single time you try and log into a foreign machine. So you can type SSH-add, the key name, it'll ask you for your password if you've got a password on your key. Once that key gets authorized with SSH-add, the SSH agent will automatically authorize that key to be used with the password with every attempt you make to log into a new server. And you can check if it's running with this eval argument here. So you can specify a lot of information in the SSH command string that will do some really, really specific work, whichever way you want to configure it. So in this string, I'm authenticating to this computer here, it's root. This is the destination, or we're doing the work via this computer. And we're going to log in using that specific key, my special key. We're going to move a log file to another directory and rename it. And then we're going to ask the local command prompt, who am I? This command here will move the log file, and it will also ask the computer what the user's name is, and it will return root because we logged in as root. So we can also send around files using SSH, but it doesn't specifically use SSH. It uses a second service which uses SSH to communicate across SSH tunnels, which is SCP, secure copy. In Linux command line, copy is CP. With SSH, secure copy is SCP. So I'm not going to run through the commands explicitly because you can kind of make out what's going on. Wherever there's a green, this is what is your local machine, and the red is talking about a foreign machine. So specifying a port number is not required if your server uses port 22 as well. The reason I've included each of the ports in a lot of these commands is just illustrative to show that you can also include a P flag with a port number. Do any of you guys know what port 1337 is about? Is what you were laughing about earlier? No? Port 1337? Elite. Yeah, it's like the elite, you know. Yeah. I'm here all night. Try the veal. So if the public key is set up correctly and the private key is in the SSH agent, this command here will work just fine. And also providing that the user of this foreign box here is also called what the same user is on the local box. If I'm often going to be using the same commands to do stuff all the time, I don't want to be retyping those commands over and over again. So for example, if I'm always logging into the same box using the same address, the same username, the same port, the same identity key, I really don't want to be like typing that long string of commands out all the time. So what SSH provides is something called a config file, which is a user config file. And you can jump into this file and you can edit in a whole bunch of things that will configure all this for you. It makes it very easy. The bad thing about this file is when you get it, it's empty. So you can drop in sort of your Git, if you use Git, like GitHub or GitLab, thank you. You can put those keys into here as well so that it will choose those keys explicitly when you try and log into GitLab or GitHub. So this is what the SSH config file kind of looks like. And so what you want to do, you want to put in all the host names for all the places you want to connect to. The host is basically your friendly name for this particular box you want to connect to. The host name, the next line, is the address that you want to use to connect to that box. Also, you don't just need to use IP addresses, you can also use domain names. So if you have an SSH server running on yourdomain.com, you can also address this in the same way. And then provided a port number, and then also, they didn't turn out very well at the bottom, but so the reason why you might want to have a host star is host star means no matter which one of these I connect to, apply all of this block to that connection as well. So if I say SSH my home PC, it'll choose that IP address and that port number, but it will also dump in my username, my identity file, and then it'll say server keep alive, and a few of these other ones as well. These are important to use if you want to maintain a connection for any more than a few seconds, because by default SSH has some timers that will roll on, and after a few seconds or a few minutes it'll actually just dump the connection, so you'll have to re-authenticate every time, which makes it even more annoying. But with this command here, you can keep the connection alive, and the bottom one actually says secure alive. Not a lot of people know about this command or this argument. You can choose to have secure alive yes, which will send these TCP keep alive messages rather than being in the clear. They'll get sent in the tunnel because TCP keep alive actually gets sent in clear text, weirdly. So there's an order of precedence when it comes to SSH commands, and that's the at the command line, in the local user config, and in the system-wide configuration files. Goes in the order of global, then user, then session. So for example, if you wanted to have password authentication turned off globally, you would set that in the global config file, and then if you wanted to use that later on for a specific host, you could then use that as a command line argument, or you could dump it into your config file, and then your config file would say that specific host gets that argument as well. So that's quite handy. So there's 3 different kinds of tunnels that SSH offer, and that's a local forward, a reverse forward, and dynamic forwarding. A local forward means you're creating a tunnel from your local machine out to another server somewhere else. A reverse forward means that you go out to that server somewhere else and you make a new port on that foreign box, and that then gets translated back to your local machine, which is really handy when you're using NAT. And then dynamic forwarding, which happens to correlate with something called SOX proxies, and this is what's generally thought to be, most people use it for something like when you want to channel all of your HTTP traffic down from, say for example, your browser or any other application. It'll dynamically choose ports that it needs to communicate directly to those places. Whereas the local forward will only give you one channel, dynamic will give you channels as you need them. So most tunnels that are established omit the full socket, like I was saying earlier in the original slide. But it has the same effect. If security is an issue and you don't want to have like this default 0000 port 23, you can bind that first address to a specific address being your private IP address or your local host. It's pretty much the same thing. Or alternatively, with this first address, you can actually have this as an open port to another IP address that they can bounce their connection through you out to somewhere else, and you can set that tunnel up for them, which is one of those commands that will set up to circumvent security in certain instances. So this creates a tunnel from, this command here will create a tunnel from my work PC, being this computer right here, and it will jump out to my home computer, where the tunnel then ends. But the traffic is then pointed at the final address of my home laptop. This laptop sees my home PC as being the origin of the traffic. So it's not really intuitive what's going on here, but it kind of jumps backwards and forwards. So this is a local forward that goes from my local address, which is this computer's address here. It goes out to this address. Oh, I've got the wrong slide up, I think, sorry. Oh, I've made a mess of this, I'm sorry guys. But we'll move right along. This one I think is the right one. So yeah, starts out at my local address. This jumps out to this VAR address and then creates a tunnel, a reverse tunnel, back to that 127 localized address. So then we have the SOX proxy, which is here. This just creates a dynamic forwarding where the service will, as the application you have this tied to needs ports, it'll generate those ports by itself. It's important to know when using SOX proxies that your DNS isn't going to be sent in the tunnel. That has to be separately configured. So I've got a short list of other use cases for SSH that I'm going to run through quickly. Tor SOX. You can use Tor through SSH, so you can jump through remote hosts first before you jump into the Tor network. I wouldn't know anything about that, but you can do it. Amazon EC2. So we do this here at Managed Services reasonably often. So you can jump into an EC2 instance, you specify the key, the IP address of the box on Amazon, jump right into that. Ordinarily, you're jumping through a Bastion host to get to those though. So jump hosts, jump hosts, this is also one of the more powerful, and it's kind of the same as what I was saying earlier. This is where you can really circumvent security with this as well. But if you want to get access to another device in behind a NATed environment, you can use this command to jump through a publicly available box and then pivot into other boxes that are in that environment. So I can jump from my work computer back into my home box, and then from there I can choose the local IP address, the private IP address of my local computer by SSHing into that one as well. And you can chain together these hosts that have to be called to reach the destination in your config file. Each of the boxes you need to touch on the way through have to be listed out. But once you've done it once, it's set and forget. So in this case, if I've got a final box, which I've just called final box in this instance, residing at this private IP address, which is behind a NATed service or behind a Bastion that I can't get to from the public internet, I can then use host 1 and host 2 and host 3. I can jump through each of those to get to that final box, provided I list out each of those hosts below there, and it will jump through there. Interestingly, you can, if you're behind a service, you're behind a Bastion yourself, and you can't get out to the public internet, you can actually SSH into that Bastion, out to the public internet, SSH across to a third box, and then into another Bastion and communicate with other computers in behind there. So you can literally jump all the way through, no problem at all. That's a good question, mate. Yes, it will. So you might have thought that SSH can't use MFA, and you would be wrong about that. You can use certificates to limit the amount of time that an SSH key can be used for. You can use Google Authenticator, and you can also use YubiKeys, no problem. Streaming video, you can stream a video across the internet using SFTP. SFTP is the secure FTP protocol, which also uses the SSH protocol. And you can do that without downloading any files at all. It'll just stream through. And SSH's old nemesis has come back to keep on capturing your data. You can do Wireshark over SSH as well. So you can also see here you can compress data before you want to move it around remotely. You can send a command that will tar compress files on a remote server before you choose to chain that up with a SCP. You can even stream the audio from one computer to the speaker of another computer somewhere else remotely using an SSH tunnel, which I think is pretty cool. I don't know why you'd want to do that, but it sounds pretty fun. And finally, last but not least, you can remote mount a file system into your local box as if that remote file system is residing as a folder on your local computer. So I can use a hard drive in my house, and I can mount that hard drive locally on this computer so it looks like that file system is located here, which is pretty groovy, which I will do later on. Does anybody have any questions? Or are you all as horrified as these people? Yes. Yeah. Oh, I can make them publicly available later on. Just come and talk to me afterwards, and I'll get your address. And yep. Does anybody have any interesting use cases for SSH they've seen or done? Go ahead. I'm using it for VNC. I have that set up in my computer as well. I have forward set up. For the recording, can you repeat? Yeah. So using it for VNC. It's very simple to set that up. You can add that to your config file. Yeah, I'm just explaining for everybody else. Yeah, so you can add the VNC ports to forward those VNC ports back to your local computer, and then you can load up VNC locally, and you can port into VNC on another computer, so you can see everything down a secure tunnel. Actually, VNC is not secure either, so you are way better off tunneling a VNC through a tunnel back to your computer. VNC also, for you guys that don't know, is like a remote desktop. It's a way you can log onto a foreign machine and use it as if you're right in front of it with a mouse and a keyboard. Yeah. Parallel shelling, yep. Oh, yep. Oh, right on. Yeah, okay. Cool. Yeah. Anybody else? Any questions at all? Like, some of this got pretty high level quickly, and then other parts of it are really straightforward. But if you've got any questions at all, come and see me afterwards. And thanks very much for coming along. Cheers, guys. So we'll take a short break now to grab some drinks, a bathroom break. Pizza's still in the back, and we'll get going with the next talk in probably about 2 minutes. Thank you.